next speaker is Luke Fay. Luke is a Senior Staff Systems Engineer for Sony Semiconductor's Component Solutions Business Division in San Diego. He has 17 years of experience in digital communication systems engineering and receiver design. Luke received an MS degree in electrical engineering from the National Technology University. That's in Japan. What? Colorado. Okay. Luke is chair of ATSC TG3 Specialist Group on the physical layer for the ATSC 3.0. The physical layer focuses on the transmission aspect for the next generation DTV standard. In 2015, Luke was the recipient of the ATSC prestigious Lechner Award.
So I'd like to start off by saying that this physical layer of ATSC 3 is brought to you by the entire world. That's no pun intended. Basically, as you saw in Skip's slides, planning for ATSC 3 started in 2010. And in 2011, things really got targeted by the ATSC to figure out what do we want to do. And we started listing exactly, these are the things we require from all these broadcasters. And when we were building the standard, we set out a call for proposals in 2013, and the response was overwhelming. So what you're about to see here in these slides is the result of basically 5 to 6 years of hard work from worldwide participation, and worldwide meaning Europe, US, China, Korea, Japan, and many other places where experts reside in broadcasting industries. They all came together to help ATSC out. So it's been a fantastic ride to actually build something where it's world-driven and everyone can play. So this is the first time you've seen this slide here. This is the system layers of ATSC 3.0. And at the top you have applications, as it goes down to presentation, protocols, transmission, and at the bottom there in the dark blue is systems discovery and signaling. And I'd like to point out, I don't have a laser here, but there is this common up arrow of signaling between each layer. And that's very key as we look at how technology evolves. We like the ability to change as we go forward. So if there's a new codec, the next generation of HEVC, for example, broadcasters would like to simply swap out that codec and use a new one. And the best way to do that is to simply signal. This program is brought to you in HEVC coding, and some broadcasters would have a different signal say, nope, this is the next generation. And so it's that ability to evolve over time that makes this very powerful. Now what I'm going to be talking about is the bottom two pieces there. So the system discovery and signaling and the transmission. Now this has arrows going upward into applications, but in reality how we build up the actual emission, everything is signaled down into the physical layer. And so it's basically the physical layer is taking everything you have and shoving it out to the emission. So this example on the left says we're sending bits over the air in 6 megahertz, and we're using orthogonal frequency division multiplexing, i.e. OFDM, to do it. But the bottom key piece here is the system discovery and signaling, which is very unique. So taking those two boxes and expanding it out on the transmission side and showing the flow of data, you now see the arrows going down. But the layers there are the same. So we have ALP processing on the top left hand corner of this slide. That ALP processing is basically encapsulating IP packets or transport stream or generic kind of packets, anything that the future might hold. It's basically meant as a wrapper, and you're going to hear more about that from Rich, who's right after me. But what he sends the physical layer is basically those ALP packets. And this A321 is the ATSC standard name for the Bootstrap, and A322 is the standard from ATSC dealing with physical layer, the waveform itself. So this is the piece where what we have standardized. This basically gets shoved down into RF processing. That is your high power amplifier, your mask filters and whatnot, to final emission over the air. So like it says on the right, there's high layer data traffic, and one of the big key things from ATSC is that it's an IP protocol, and you're going to hear more about that from Rich as well. But it takes in packets, generic size packets from ALP, and then sends them out the back. For your reference, I've put the locations of these standards here. I'll take a little bit of break to show you that if you want to jot it down. But these are the HTTP URLs for these standards: A321 top, A322 on bottom. But basically, if you go to www.atsc.org, you can see these standards there under the candidate standards. Or actually, this is under standards now, ATSC 3 button on the web page. So back in 2010 and 2011, we were developing requirements, and all the many broadcasters came together, and they said, we need a means to broadcast bits. And it's no longer just to a stationary device or a mobile device, it's to a device and all devices. We're not distinguishing between stationary and mobile anymore. And it has to have an efficient use of spectrum. Technology has evolved, and better utilization of the frequency space is possible. So we want to drive in that direction. It's basically called the Shannon limit. We want to get as close as we possibly can to that. We want the ability to control robustness. If I want to target all devices, I want to have some with a higher quality of service than others, and I want some with a higher capacity of data than others. So the ability to select different operating points in my single emission to match business needs is a must. There's no budging from that. And we need to utilize multiple operating points simultaneously. So I want to target mobile, and I want to target stationary, and I want to target different kind of devices all at the same time. We also need to reach all devices. So in America and all across the world that I know, we have urban canyons, we have rural settings, we have people in cars, we have people deep indoors, like this place here. And we are targeting all places for reception. So it's deep indoor reception for stationary devices. It's also reception to cell phones everywhere they go, even in high-speed trains or cars. So from a large screen with rooftop antennas to handheld portable devices, anything in between, we want to get service to those devices as people start to use the technology. They're getting used to just picking up a phone and finding out the answers to their questions. And if they want to find out the score of the current game, they can do that. Well, broadcasters are going to make that happen as well. So here is a comparison to what we have today. On the left-hand side is ATSC 1, and on the right-hand side is ATSC 3. So on the left, we had one bit rate, 19.39 megabits per second, and it requires 15 dB, roughly 15 dB SNR. And the service flexibility basically was set for HDTV and multicast and data. So if I'm going to draw a blue circle like you see at the bottom left-hand there, the intent of that service was to have a broadcast tower emit to a certain coverage area. That coverage area is in blue, and that antenna off to the left there is meant to show a masted antenna 30 feet in the air as a model, and covering that 19.4 megabits per second. So the technology that used that, that provided that was 8 VSB, that's 8-level vestigial sideband modulation, which was mainly brought to you by LG. Thank you, Wayne. And it used Reed-Solomon encoding on the FEC to provide. So that's what we have today. For the right-hand side of ATSC 3, we're starting off with a bootstrap symbol. And that's basically a very robust key to start the signaling process. And it's the key to system flexibility. And it basically signals a preamble of a frame which can carry more bits per second per hertz, which is more efficient near the theoretical limit. And it has a flexible bit rate and coverage area of choices. So it enables the on-channel repeaters of SFN. Basically, with OFDM technology, it's no longer a concern of echo cancellation when you're setting up single frequency networks. It's just a matter of power add for OFDM. So you have much less headache when you're rolling out an SFN. And basically, we're providing simultaneous physical layer pipes. I'm going to get into that just a little bit. But basically, if I'm comparing the two circles on left and right, the blue circles, they're the same size, believe it or not, but the number is different. So using a 15 dB SNR with the same power and the same antenna size as ATSC 1.0, I now get 25 megabits per second. So we've become much more efficient, okay, and more robust. And with these multiple physical layer pipes, if I want to add mobile devices, I can. And with a higher quality of service or a lower bit rate targeting these mobile devices, the coverage area now expands beyond that. But not only does the coverage area expand beyond it, it goes deep indoors. It's a more robust signal. So it's getting deeper into urban canyons. It's penetrating deep indoors for cell phone reception in this building, for example. So I wanted to make that clear that we're targeting multiple devices here. Okay, the key. If I look at the top right hand, you have that golden bootstrap key. And that's kind of a figure in your mind I want to make. Is that this is the starting point. This is the key to the door that unlocks your payload. And it's a key to the change of the physical layer. So I've titled this Entry to Evolution. So if you want to change from ATSC 3.0 to ATSC 3.1 or 3.2, whatever it is, you will always start with this bootstrap key. And the key will tell you what you're signaling. So it is the robust universal entry point, and it signals a minimal set of parameters. And basically the minimal set is a priori information. And if you're in the world of digital communications and signal processing, you know that channel bandwidth and sampling frequency should not change when you're building a device. It should be known a priori that you can just build a device and expect it to work. That's not what the broadcasters wanted. They wanted the ability to change that on the fly. Well, change that when needed, I should say. And so what this bootstrap key does is send or signal what is the channel bandwidth, what is the sampling frequency, and it also includes emergency alert. Is there something that you should know about right now? Very robust information is what this carries. And what I mean by robust is that it's less than -6 dB SNR required for reception. Okay, that's 4 times less power than the noise in your environment. 4 times. If you sped up a spectrum analyzer and looked at the frequency spectrum, you would not see this. It's below the noise. That's how robust it is. So, like I said, it includes emergency alert, and it is attached to the beginning of a physical layer frame. So the bottom graphic there is a frame of ATSC 3.0. And the colors are intended there. So we have a gold bootstrap key on the top right, and we also have that gold colored bootstrap box on the bottom left. That bootstrap basically is having a little arrow there at the top pointing to L1 basic, and that's exactly how we've structured a frame. It's hierarchical signaling. So we have a very robust starting point. Here's your sampling frequency and your channel bandwidth. Now go here for the next bit of information, which is L1 basic. L1 Basic says, here is the basic FFT size that is going to come out, and here's the guard interval that's going to be used, et cetera, et cetera. And then that points into the preamble saying, okay, here's how many subframes there are, and here's the pipe structure, and here's the scattered pilot patterns, et cetera, so that receivers can go step to step by step to decode the frame. The architecture is shown right here, but to make it feasible, I've had to use a lot of acronyms. And I've had a little decoder ring at the bottom right. You see, believe it or not, if you're a fan of A Christmas Story, you know that synchro decoder ring, and he's going through it. Well, that's kind of what this is. It's an acronym list, and the spelling out of each acronym on the top diagram there, so you can figure it out. One of the things that I wanted to point out here is that there are two pieces of the physical layer. One is at the studio, and the other one is at the transmitter. So if any of you are familiar with OFDM demodulation, you'll see very familiar blocks. Here you'll have a scrambler, an FEC, which is forward air correction, a bit interleaver, a mapper, which is your basic chain for starting up and outputting symbols of OFDM. But there is a new box called layered division multiplexing, and that's a new technology that's come out. Basically, it's superposition of powers, and it's a different form of compacting information together, and I'll talk a little bit more about that in a second. But you can see that as we move on, it goes into some MIMO technology that you're targeting, some framing, frequency interleaving, pilots, MISO, inverse FFT, and out the back for signal processing. So what does this do? Well, here's a simple list of functions. We have payload scrambling, low density parity check, forward air correction, FEC, bit interleaving, non-uniform constellations. It's no longer those square constellations that many of you might be familiar with in cable environments. It's funky patterns that look weird or cool, depending on who you are. It's actually an improved performance when you bind those non-uniform constellations with LDPC to get very robust transmission. This is a Shannon curve, if you're familiar with those. The Shannon limit is the blue line. Don't even think about operating on the left-hand side of that. It's physically impossible. The Shannon limit basically is bound by Nyquist criteria, there are arguments against people saying that they can beat Shannon. Shannon was based on Nyquist, but I'd like to see you try to beat Nyquist on that. So I see a thumbs up there in the back. Shannon is it. That's it. And one of the cool things about this slide here is that picture at the top right-hand corner. It looks like an entire fuzzball. It's not. That's actually converged 4096 QAM. And it takes 30 dB SNR to do it. But when I was mentioning the non-uniform constellations, the picture in the middle there, that is the 256 QAM constellation. And it's not really square, it's kind of an oblong thing. As reference, I've included ATSC 1.0, otherwise known as A53. I've labeled that there. And you can see DVB-T2 is labeled in green, and the operating points of ATSC 3.0 are in red. So we're very, very close to the Shannon limit. If you look at it closely, there is a gray line which basically is the BICM limit. And when you combine bits into symbols, you have that BICM limit. That's another one of those curves and lines that you cannot cross over. And if you look closely at it, you'll see that the ATSC 3.0 line rides on top of those gray BICM limits. If you want to use this service, you want to have low capacity or a high robust signal, you go on the bottom side or the left-hand side of this curve. If you want high capacity and less robustness, you go on to the right. That's the way it works. Okay, physical layer pipes. So when we're targeting multiple devices, we want to have different quality of service for each frame. That's the simultaneous delivery. So the way we've done it is to set up physical layer pipes, PLPs, that can be configured differently. One can have that high robustness, one can have that high capacity. And they can be configured on a per subframe basis. So the robustness versus data capacity trade-off can be done for each one, and they can be arranged in patterns of frequency and time resources there. So in subframe 0, we can have 3 pipes that we can configure, and we're targeting different devices. And in subframe, or the last subframe, we can have 1 big fat pipe, and we're only targeting a stationary device, for example. Okay, so it's very, very flexible in what you can do. Let's see, there are up to 64 active simultaneously in a single RF channel. That's from the broadcaster itself. But in receivers, it's not expected that a device can simultaneously decode 4 at a time. It can simultaneously decode 4 at a time maximum, up to 4. Yeah, I did say that 4, okay. So when I'm looking at what can I do here, going back to that curve of multiple operating points, the time division multiplexing, or TDM there, can operate anywhere along that curve. Any red dot you can set up as a time division multiplexed. And you can set it up with different physical layer pipes. So what I'm showing here is, well, right, that big fat black star, that's the ATSC 1.0, and the red dots are ATSC 3. The smaller, I don't have a laser pointer here, it's killing me, but the small black dots are A153, which is the mobile ATSC. That's a little bit better at the bottom there, but ATSC 3 does beat it. So when I'm setting up a service, we can also have this layered division multiplex scheme. Now, layered division multiplexing really is advantageous with higher SNR. So while I'm showing 2 different arrows here, one off going up the curve and one going down the curve, it's really advantageous up around 15 dB or higher. That's where LDM really excels in efficiency. However, that's not the only point that LDM provides. It can also be very, very robust. So it's a matter of choice what the broadcaster wants to do. If he wants to have high efficiency operation, he'll operate LDM higher up the curve, around 10 to 15 dB SNR, or he can target very robust devices down at the bottom, and that's basically in the 0 to minus 6 dB region. As a matter of reference, I think LTE operates in the 3 to 5 dB SNR range. But LTE is a totally different animal. They got a small cell structure and whatnot. They can operate in smaller area and with smaller powers. Thinking about service, what are example scenarios of what we can do? ATSC did due diligence. I think I got about 5 minutes. And tried to figure out what are probable use cases of this technology. We have so many choices. What are some combinations of reality that people have interest in? And that's what we've listed up here, and there's 4 of them that I listed up. So hopefully you can see it. I tried to blow it up as best I can and still provide as much information. But the first one is ultra high definition TV with a single stick time division multiplexed service. Basics kind of service as we have in ATSC 1. And basically I've had that aerial antenna off in the middle there, that middle column, showing what are the bit rates. The channel loading column shows a lot more detail. For this example, it's using 2 pipes, a PLP1 and a 2, with different it has a 32K FFT and certain guard intervals, and it's set up with certain PLP capacities. The second row is a multicast, high definition, or SD, and it also targets, it also uses time division multiplexing. It also targets the stationary device with a high aerial antenna, but this point here is 2 to 4 high definition services. So it's not really targeting ultra high def, it's just HD, but with all this capacity available, you can do 4 service programs at a time with this configuration. But some people will say, no. I'm not caring about stationary anymore. I want mobile. I want to go to a mobile device. I want to get deep indoors, and I want to reach as many consumers on the mobile device as possible. That's scenario 3. which we're calling deep indoor high definition. And this is using layered division multiplexing. So we have, I think it's a 6 to 8 injection level there is -3 dB, but there's like 6 to 8 services there, and we're targeting a fixed and portable deep indoors receivers. And I've labeled it with a smartphone kind of diagram there instead of an aerial antenna, but this on the two pipes on the bottom row there in the green, the aerial antenna, believe it or not, is shoved in the middle of the text there in the top kind of sub row there in green. But basically, you can have a stationary device operate with a PLP1 and having a capacity of about 6 megabits per second and still operate at about 10 dB or 11 dB SNR for a relay channel, which is better than the 15 dB today, and yet still targeting the mobile devices there, and it shows a relay channel of 1.45 and negative 0.5 dB SNR operating point for a secondary audio on a mobile channel there as well. So you can set up a stationary device requiring less SNR today for ATSC 1.0 and mobile devices operating at points within an LTE range, if not better, and still have, say, oh, I have an even secondary audio device, or a secondary audio service come to those mobile devices with even better robustness, very, very robust audio. So this green row is of interest. It's a highlight of ATSC 3.0 when you can target everything. And the last one there, row 4, is deep indoor with mobile SFN and time division multiplexing. This is when you set up an SFN. SFN basically adds more power to your market. And with that higher power, as it shows here on the last graph, I believe, one of the two, if you receive higher SNR, you can operate at higher points along the Shannon curve. Okay? And the more SNR you get, the more capacity you can deliver. So in SFN, if you choose to roll that out, it would deliver a higher capacity payload to all devices. It says here the LDM will allow reception at lower SNR in more challenging environments with less impact on the total channel capacity. So that's the doubling up of superposition there. So it just depends on what you want to do. Hopefully these use cases give you some ideas of what you want to do and how you want to actually use ATSC 3.0 or build out your business models. But this technology basically is the kickstart to allow business opportunities to happen and business thoughts to come together and say, this is what I want to do. Can I do it? ATSC 3.0 should allow you to do that technically. We're removing the technical argument from it. So in summary, we enable many system options for the broadcast industry. We have a hierarchical control signaling of the physical layer. It's very robust. It's very efficient use of spectrum. It's very flexible in its configurations with a large SNR range, allows many choices of robustness and high capacity, and it's all started with a very robust synchronization key, which we call the bootstrap, I'm sorry, to allow for future evolution of technology. We start with that key. Many flexible functions, and we look forward to providing a recommended practice with this, with further information of, okay, here is what we're actually seeing with initial hardware. So be on the lookout for that recommended practice. And with that, I'll turn it back to Wayne.
Panasonic.